Hello everyone, I am Yanchen Liu, a PhD student at Northeastern University. Today I'm going to talk about network symmetry. So first of all, what is network symmetry? Here I'm showing 3 examples of networks that are intuitively symmetric to us. So the next question is, how do we formalize our intuition that they are symmetric? An important step in formalizing a network symmetry is that noticing that there is a common feature in these networks, which is that there exists sets of nodes in these networks that are equivalent to each other, which in other words means that they can be interchangeable to each other without changing the network structure. Formally speaking, if a network is perfectly symmetric, then there exists a node permutation P which permutes node I to Pi that preserves the adjacency matrix of the network. Such node permutation P is called an automorphism of the network. For example, in this example network here, there exists such node permutation which permutes node I to 2, permutes node 2 to I, 3 to 4, and 4 to 3. And after node permutation, the network stays exactly the same. Specifically, preserving an adjacency matrix means that if there is an edge between node I and j before permutation, which means that aij is 1, then there is also an edge after node permutation between node pi and pj, which means api pj is 1. Similarly, if there is no edge between node I and j, then there is no edge after node permutation between node pi and pj. A node permutation P can be represented by a node permutation matrix P. So for example, in this node permutation that is represented on the left, it can be encoded in the matrix on the right. So in this matrix, there are 4 non-zero elements here, P12, P21, P34, P43, which represents permuting nodes between node 1 and 2 and 3 and 4. So now that we have a definition for perfect network symmetry, the next question is that enough? Here I'm showing 4 examples of networks. The first network is a 2D lattice network, which is perfectly symmetric. It has a perfect symmetry, so it will be classified as symmetric. The second network, however, is the first network with one missing edge. So if we only consider perfect symmetry, then this network will be classified as asymmetric. However, intuitively speaking, we still feel like there is a certain level of symmetry in this network, even though it doesn't have a perfect symmetry. In the third network, it has a perfect symmetry because it's a ring lattice. However, in the fourth network, it's the same network with 2 missing edges, which makes it asymmetric according to the definition of perfect network symmetry. So this prompts us to come up with definition for not just perfect network symmetry, but also approximate network symmetry. So why is that important? Why is approximate network symmetry important? It is because that, especially in the cases of real-world networks, perfect symmetry for especially a large set of nodes and edges imposes a very strict limitation that is hard to be met due to the stochasticity of networks, especially for real networks. So how do we measure approximate network symmetry? Here, for example, is a network that has a high level of approximate network symmetry but no perfect symmetry, and this is its adjacency matrix. Now let's do a node permutation for this network, which permutes the upper half of the network to its lower half. And here is the network after node permutation. Notice that one edge in the original network in the circle there is not preserved after the node permutation in the circle in the permuted network because it doesn't exist anymore. And this permuted network has adjacency matrix PA-P transpose, where P is the node permutation matrix. And note that these two adjacency matrices have different non-zero elements, and the absolute difference between these two matrices is 4. So in this node permutation example, one edge is not preserved, and the absolute difference, which is the norm 1 difference between A and BAP transpose, is 4. So this means that each unpreserved edge is represented by 4, a difference of 4 in the two adjacency matrices before and after node permutation. So this gives us a way to measure approximate network symmetry, which is defined as EA, which is minimizing over different possible node permutations that minimizes the difference between adjacency matrices before and after node permutation. So this EA effectively means the least number of edges that are not preserved in any possible node permutation. So if a network is perfectly symmetric, it has EA equals to 0 because we can always find a node permutation that preserves all edges in the network. And the more symmetric a network is, the lower its E is. Also, we can normalize E by 1/2 of n choose 2, and the reason behind this is because after this normalization, SA is always less than 1. So after we have this, now that we have this definition of network symmetry, we applied it to 4 different network models as well as several real-world networks. First network model is ER network. So here we are measuring ER network samples from G and M ensembles with n equals to 100. So first of all, here we can see that when m is 0 or n choose 2, they always have s equals to 0, which means that for empty graphs or complete graphs, they always have perfect symmetry. And s reaches its highest when m is 1/2 of n choose 2, and also this curve is symmetric around the middle point, which suggests that ER networks from ensemble G and M and G and n choose 2 minus m have the same level of symmetry. This can be proven rigorously, but I'm not going to do that here. The second model that we looked at is the random geometric graph. Here we're showing s as a function of m as well as the connection radius r. And we also showed s for ER networks as a comparison. So we can see that RGGs with or without periodic boundary conditions are always more symmetric compared to ER graphs. On the right here, we're showing 2 examples of RGGs without periodic boundary conditions at a lower and a higher connection radius. So one interesting thing is that at r equals to 0.3 in the node permutation matrix P on the right here, most of the non-zero elements are located around the diagonal of the matrix, which means that a node is very likely to be permuted to another location that is very close to its original location. This can also be observed by looking at the node colors in the permuted network. As you can see that the node colors are not that different from the original node colors, which means that only local permutations are made. The third example is Wasserstragas networks. Here we measured S as a function of the number of edges M as well as the rewiring probability P. And we can see that Wasserstragas networks are less or equally symmetric as ER networks. And as the rewiring probability increases, more and more edges are rewired, the Wasserstragas networks become more and more asymmetric until it becomes indistinguishable from an ER network with the same number of edges, and its S saturates to that of an ER network. On the right, we're showing 6 examples of Wasserstragas networks with fixed number of edges but at different rewiring probabilities. We can see that at low rewiring probabilities, the node permutation matrix is very orderly, either shows a rotation of all nodes as a whole or an approximate reflection plus a rotation of all nodes. When the rewiring probability is high, we observe an interesting phenomenon, which is that a part of the nodes are rotated as a whole, part of the nodes are reflected and rotated. and when p is 0.55, the network is basically as asymmetric as an ER graph, which can be observed in the node colors in the permuted network, and as well as the node permutation matrix, which is pretty much random. The fourth model we looked at is the stochastic block model. So here we observed a very interesting effect, which is that the communities in an SBM network are very similar to each other. Therefore, in the optimal node permutation matrix, we can see that the nodes from different communities are actually switched. So in the first example, when there are two communities, the nodes are switched. When there are three communities, two of the communities are switched, whereas in the third community, the nodes are mainly only scrambled. At last, we applied our measure to some real-world networks. The first one is the C. elegans brain network, which nodes are colored based on which hemisphere they belong to, and we can see that after the node permutation, most of the nodes are permuted to the opposite hemisphere, and on top of that, a lot of nodes are actually permuted to their counterparts in the other hemisphere, represented by the non-zero elements on the diagonals of the diagonal 2 blocks in the P matrix. And the second example is the macaque brain network, in which each node represents a brain region in the network. And we can see that this network, in fact, has really, really high bilateral symmetry, whose node permutation actually flipped the two hemispheres of the brain exactly. And note that even though the two hemispheres are flipped exactly, its E is 11.99 instead of 0, which means that the two hemispheres of the brain are actually different, slightly different from each other, which means that the network does not have a perfect symmetry but has a high level of approximate symmetry. And this is a good example of why having a definition of approximate symmetry and the measure for approximate symmetry is important.